Kuji Bismillahirrahmanirrahim. Welcome to another lecture of modern control systems. Today we are going to study Routh Hurwitz criteria for stability of a system. Routh Hurwitz criteria for stability, which is also called RH criteria. So what basically is the purpose of Routh Hurwitz criteria? Up till now, if someone asks you how to find the stability of the system or tell us whether the system is stable or not, all you know is find the roots of the characteristic equation and plot those roots on S-plane. If those roots are on completely on left hand side, then you say that the system is stable. But if any root falls on the right hand side of the plane, you say that the system is unstable. So if you are given with a first order, second order, third order, or up to fourth order system, it is easy to find roots of the system. But if you are given with a higher order systems, so just imagine how can you find the stability of the system, because finding roots or finding the location of the roots or location of the poles would be cumbersome in that case. So we want to have something that if even if we don't know the exact location of the poles, we should at least know whether the poles are on the left half plane or the poles are on the right half plane. So for this purpose, we have this Routh Hurwitz criteria. So this RH criteria don't tell us exactly where the poles are, but it do tell us that whether the poles lie on the right hand side of the plane of the S-plane or on the left hand side of the S-plane. And from this information, we can conclude that whether the system we are dealing with is stable or unstable. So for that we have a Routh array. Let's try to form a generic Routh array. For example, if we are giving with the system numerator of S divided by A4 S4 plus A3 S cube plus A2 S square plus A1 S plus A naught. Let's suppose this is a transfer function of any system and someone asks you that tell us whether this system is stable or not. So first step is to make a Routh array. Now what is a Routh array? It is a simple process. First of all, write down the S terms vertically. For example, S4, S3, S, or rather let me try to okay, S4, then we have S3, S cube, then we have S square, then we have S raised to the power 1, and then finally we have S raised to the power 0. 3 S2 S1 and then S0. So I'm basically at the moment I am trying to make a Routh array. So now first of all you have written the maximum power of S in the denominator over here, and then write all the powers of the S in vertically in the first column. Now what about the coefficients, which are A4, A3, A2, A1 and A0 in this case? Next step is to write the coefficients. For example, write A4 over here, then in this manner, then A3 then A2. Obviously, when you would be making an array, no need to draw these arrows. I am only drawing these arrows for understanding. Then A1, then A0, then 0. A4, A3, A2, A1, A0, and then there is no other coefficient, so 0. So what would be over here? You even don't need to draw these vertical lines as well. I'm just drawing for the sake of understanding. So what would be in these blocks? This and this and this and this, and we need to fill up these blocks. So in this block, we would have minus of determinant of A4, A3, A2, A1 divided by A3. Similarly, in this block, we would have minus of determinant of this term will remain constant in all the boxes. So it would have A4, A3, then next term is A0, A0. Use A0, sorry, 0. A0, 0 over here, and then A3. This A3, this A3, this A4, A3, this A4, A3 remains same. Let's call this as B1 and let's call this as B2. Similarly, in this column, we would have minus of A4, A3, and there is uh, no other term left over here, so it would be 0, 0 divided by A3, and let's call it B3, which would be actually equal to 0. So now there are no other terms left, so we will stop over here. There is no need to go further. So let's go to this row. So what will come over here will be minus of A3, this one, and then this B1, A3 B1, and A1 B2 divided by B1. Let's call it C1. Similarly, I think you might have guessed that what would be over here. It would be minus of A3B1, same as over here, and then here we have after A1B2 we have this 0, 0 over here. This is 0 and this is also 0. So we will put up 0, 0 over here divided by B1, and let's call it C2. Similarly, over here we would have A3B1 and 0, 0 divided by B1. This will also be 0. So finally, in the last row, we would have minus. I hope you people would have guessed. Just pause this video for a moment and guess what would be what should be written in this box. So in this box, we will write B1, C1, B2, and 0 divided by C1. And here I will write minus of B1, A1, 0, sorry, C1, it is not A1, C1 divided by C1. And here I will write minus of B1, C1, 0, 0 divided by C1, which is equal to 0. So our Routh array is complete. What we have done, we have simply written all the powers of S in the first column, and all the coefficients in first two rows over here, and then filled up this Routh array by a typical formula that A for determinant of minus of A for A3, these two terms and these two terms, and for next we have these two terms and these two terms, and for next we have these two terms and then terms over here, these two terms, and all are being divided by this A3. Similarly, in this everything is divided by this B1, and in this everything is being divided by this C1. So you should have a brief idea that the coefficients in the first column, the coefficient in this column, in the first column of Routh array are very important, because if any of this coefficient is zero, then there would be a problem. We will see how to tackle that problem later in this lecture, but you must have an idea that this all row is dependent upon this A3, and this all row is dependent upon this B1, and this all row is dependent upon this C1 because it is in the denominator. So if A3, B1 or C1 is 0, then obviously these terms would be undefined or infinity. So in that case, how we will find the uh, stability would be a question mark. So step one was to make a Routh array, which we have already done. Step two is to observe. Let me use another marker. Step two is to observe this column. If there is if there is no sign change in this first column, I will say that your system is a stable system. So actually, the number of sign changes is equal to number of uh, poles on right half plane. For example, if this term is positive, this term is positive, this term is positive, this is positive, and this is positive, all a 1, 2, 3, 4, all of these five terms are positive, then we will say that our system is stable and there is no pole on the right hand side. And if this term is negative, every term in this column is negative, then still there will be no sign change and your system would be stable, and all poles will be on the left half plane. And if this term is positive, this is negative, and then again this is positive, it means that there are two sign changes. One is this positive, positive, negative, positive, positive. It means one sign change is from positive to negative, another sign change is from negative to positive. So there are two sign changes over here. Two sign changes means there are two poles on the right half plane, and hence the system is unstable. So this Routh array has the capability to give you insight without even calculating the roots of your characteristic equations. It can tell you that whether the poles of the system are on the right half plane or not, just by uh, inspecting the first column of the Routh array. So what if there is a 0 in the first column? So now let's have few scenarios. Let's discuss few scenarios. Scenario number one: what if we have a 0 in first column? Because if there is a 0 in first column, then it would be obviously impossible to draw or to write the Routh array, because that 0 term would make all other terms infinity. So how we will proceed with writing other terms in the Routh array is a question mark. So in that case, when we have 0 in the first column, for example, uh, let's have a transfer function t of s is equal to 10 over s5 plus 2s4 plus 3s cube plus 6s square plus 5s plus 3. So when we will try to write the Routh array of this system, which will be s5, s4, s3, s2, s1, s0, and over here you will have 1, 2, 3, 6, 1, 2, 3, 6, 5, and 3. So what would be in this column? Let's try to find this box. This box would be minus of 1 2 and this 3 6 divided by this 2, which is 6 minus 6, which is actually 0. So I have 0 over here. So if I have 0 over here, I cannot proceed with filling the remaining uh, remaining entries of the Routh array. So in this case only we have a 0 at this first column. We may have any other term over here and we may have any other non-zero term over here. We are not considering the case that we have uh, all the terms of the row equal to 0. At the moment we have only 0 in the first column, and these terms may or may not be 0. For example, let's try to evaluate this term. This term will be okay. Mm, let's make some space over here. Okay, if I try to find the second term, which is minus of 1 2 5 3 divided by 2, which is equal to minus into 3 minus 10 divided by 2, which is 7 by 2, which is actually a positive term. So in this case I don't have a complete row equal to 0. I only have, in this case number 1, I only have my 0 in my first column. So in this case obviously if I have 0 in the first column, then there would be problem to fill this the entries of s square row, the entries of s1 row, and the entries of s naught row because of this 0. So what to do, what to do? So the step we should take is to assume this 0 as a very small number, epsilon, and then continue your calculation. If I have this number as epsilon, and this my s square term over here will be 6 epsilon minus 7 divided by epsilon. Similarly, obviously there will be term over here in term of epsilon, and there will be the term over here in terms of epsilon. So if I take epsilon equal to 0, then obviously this term will be infinity or undefined. I would not be able to fetch out any result from my Routh array. So I assume that this is not exactly equal to 0. This is some small value epsilon, and then I proceed with my calculation with this epsilon in place of 0. So then afterwards, I assume that what if epsilon is a small positive number or epsilon is a small negative number. You may say either it is 0.001 or minus 0.001. For example, let's take it as an example. So we will first of all we will replace this zero with a very small number epsilon and then continue our calculation with epsilon in place of that zero. Then we will assume that let's take this epsilon a very small positive number or it may be a very small negative number. If it is a very small positive number, then this one, the entries in this column are, this is positive entry, second entry in the first column is positive, third entry I am taking epsilon as a small positive number, so I will take this entry also as a positive entry. For this entry 6 epsilon minus 7, this is a very small number multiplied with epsilon, so obviously you can see that it would be a negative number. So let's make it a negative number, and then when you will find expression of the in this place and in this place, they will be positive and positive. Similarly, when we will take epsilon as a small negative number, then these signs would be like that. Epsilon is a negative, small negative number over here, and then it is positive, positive, positive. Now you can see that the sign changes whether you take epsilon a small positive number or whether you take epsilon as a small negative number, the sign changes remain same. For example, this is plus plus plus, plus to minus, one sign change, and minus to plus, another sign change. Similarly, this is plus 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 to minus, one sign change, and minus to plus, another sign change. In both of these two cases, the sign changes are constant. So you can either take epsilon as a small positive number or you can take epsilon as a small negative number. It's up to you, because we have seen that in both cases our result is same. We are not concerned with these values. We are only concerned with the sign of our first column, because the only thing of interest in Routh array is the uh, sign changes in the first column, which tells you whether your system has any pole on the right hand side or not. So if by taking this small epsilon and then continuing our calculation we can get this information, then obviously we have achieved our goal. So how to go about it: when we have a zero in the first column, replace that zero with epsilon, continue your calculations, and then take epsilon as a small positive or a very small negative number. Put that small positive or small negative number in your expressions over here, and over here, and see whether you get a positive or a negative result. So if your results are all positive, then there is no pole on the right hand side. If all results are negative, then there is no pole on the right hand side. However, if there are sign changes as there are over here, then obviously there will be a pole on the right hand side. So I believe you are all satisfied with this case number one. Case number two is a very interesting case when your entire row is zero. In the previous case, we only had a zero in the first column, but entire row was not zero. But in this case, our entire row is zero. So how to, now we will see how to go about it. For example, let's take an example that we have a transfer function t of s is equal to 10 divided by s5 plus 7s4 plus 6s3 plus 42s square plus 8s plus 56. So let's suppose I have this transfer function. Now let's try to make its Routh array. S5, S5, S4, S3, S square, S1, S0 over here, and 1, 1, 7, 6, 42, 8, and 56 over here. So what would be over here? 42 minus into 42 into 1, 6, 7, 42. So from here I can see that there will be the 0 over here, and then 0 over here, and then 0 over here. So my this complete row is equal to 0. So now how to go about it? How to go about it? If your complete row is 0, if your complete row is 0, then you take a row above that 0 row as an auxiliary equation. For example, this row is 0 row, and this row will help you to form the auxiliary equation. So whenever your complete row is 0, you make an auxiliary equation with the help of row above that 0 row, which in this case is 7, 42, and 56. So your auxiliary equation will be 7s4 plus 42s square plus 56 is equal to 0. So this will be your auxiliary equation. We can also write it as s4 plus 6s square plus 8 is equal to 0. Next step is to differentiate this, take the derivative over s, differentiate this auxiliary equation. When we differentiate this auxiliary equation, we have 4s3 plus 12s plus 0 is equal to 0. That is s cube plus 3s equal to 0. So this is the equation that we have formed after differentiating our auxiliary equation. So now use that equation for this 0 row. Replace this 0 with 1. Replace this 0 with this 3. So there will be 1, 3, and 0. So now you can continue your rest of the calculations, which will be, you can have it at home as well, which will be 3, 8, 0, 1 by 3, 0, 0, and 8, 0, 0. So this will be our Routh array for the scenario when we have an entire row equal to 0. Now how to interpret this? Scenario when you have a complete row is equal to 0. In this case, you divide your Routh array in two portions. One is from auxiliary equation and downwards, and another is from auxiliary equation to upper end. Sorry, from this, from equation above auxiliary equation to upper end, and auxiliary equation to lower end. These are the two portions. So how many sign changes are there in upper portion? There is no sign change in the upper portion, so there is no pole on the right hand side. Concluded. Now for the lower portion, there is no sign change in the lower portion. Agreed. Now whenever there is a 0 row, keep in mind, whenever there is a 0 row, your roots are symmetric symmetric around origin. The roots of this portion, which I am uh, marking with a star, roots of these portions are symmetric around origin. Now, what do I mean with the symmetric around origin? For example, if I have one pole, then this is the symmetry around the origin. If I have two poles, then I can say this and this are symmetric around origin. If I have four poles, I can say these four are symmetric around origin, or this are symmetric around origin. Now, as you can see, there is no sign change over here. There is no sign change over here, and maximum power is S4. So it means there are four poles over here, and if there is no sign change, it means that there is no pole on the right hand side. So all the symmetry around origin would be on the j omega axis. 1, 2, 3, 4. Because there is no if there would have been a sign change, let's suppose that there are two sign changes in this area. If there are two sign changes, then we can have our four poles like this, two poles on the right hand side and two poles on the left hand side. If there are, in case of two sign changes, we have to uh, we have to fulfill this condition, symmetric around region, while uh, your uh, keeping this condition intact as well, that if there is no sign change, you cannot put any pole on the right hand side. So for this lower portion, I have four poles. Due to this S4, I have four poles, and due to the zero row, I know that all of these four poles are symmetric around a region. However, I do not have any sign change over here. If I don't have any sign change over here, then it means I cannot draw any pole on the right hand side. Now I have to draw four poles with symmetry around origin, but I cannot draw any pole on the right hand side. So the only option I have is this. The only option I have is this, because if I will draw any pole over here, then for maintaining the symmetry I have to draw a pole over here, and as there are no sign changes, so this I cannot. Therefore, I can safely assume that this is a marginally stable system which has four poles on the imaginary axis, and total there are five poles due to S5. I have four poles on the imaginary axis and one pole on the left half plane. So, from here I can conclude your system is marginally stable. I have symmetry around the origin, and for that symmetry, the poles I have, there are no sign changes for those poles, so I cannot draw any pole on the right hand side. So let's have an example, another example, which is transfer function is. I would like you to pause this video and try to solve this example by yourself, and then see if your solution matches with the one that I will write over here. S8 plus S7 plus 12, S6 plus 22, S5 plus 39, S4 plus 59, S cube plus 48, S square plus 38, S plus 20. Now imagine if someone gives you this transfer function and asks that whether it is stable or not, and you try to find the poles or the roots of this eighth order equation. Obviously it would be impossible for you to find poles for this system. So here we are with this Routh Hurwitz criteria. So S8, S7, S6, S5, S4, S3, 3 S 2 S 1 S 0. S 3 S 2 S 1 S 0. S 0. S 1 S 2 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S 3 S 4 S So what are the coefficients? 1, 1, 12, 22, 39, 59, 48, 38, 20 and 0. So let's try to write terms for this S6 row. Again, I would request to pause this video and try to fill out all the entries on your own, and then just recheck the entries with the entries that I will do over here, and then you match your results, your interpretations, that what is the location of the poles for 8 poles for this system. Where do all the 8 poles lie? So for S6 I have minus 10, here I have minus 10, here I have minus 20, here I have 10, here I have 20, here I have 0. I can write this as minus 1, minus 2, 1, 2, dividing this whole row by 10. It doesn't make any difference, by the way. So for this S5 I would have 20, 60, 40, 0, 0. Again, I can divide this whole row by 20, which would only help me for uh, making calculations simpler. So this is 2, this is 3, this is 2, sorry, this is 1, as I have divided by 20. This is 1, 3, 2, 0, 0. Now what would be S4? S4 would be 1, 3, 2, it would be same, 0, 0. Now what will be S3? 3 minus 3. Oh, as these two rows are same, so at S3 I have 0, 0, 0, 0, 0. So this complete row is 0. Now you already know how to go about it when you have a complete row equal to 0. When you have a complete row equal to 0, see the row above that 0 row and make an auxiliary equation out of it. So auxiliary equation in this case would be S4, 1S4 plus 3S square plus 2 is equal to 0. So after taking derivative, 4s3 plus 6s is equal to 0, which I can also write as 2s cube plus 3s equal to 0. So 2 and 3 are the coefficients. So I can write 2 over here and 3 over here and resume my calculation. So here I have 3 by 2 and 2, which by okay, let me write it, 3 by 2, 2, 0, 0, and then I have 1 by 3, 0, 0, 0, and then 4, 0, 0. So again pause this video. Now you have this Routh array in front of you. Pause this video and let me know that where are the poles of this system. Where are the poles of the system in S domain? So where is the auxiliary equation? This is the auxiliary equation. So I have two portions. One is this and one is this. So is there any sign change in the first portion? 1, 1, minus 1, 1. Yes, there are two sign changes over here. So I can say that there are two poles on right half plane due to these two sign changes. 1 positive, minus 1 negative, one sign change, and then again 1 positive, second sign change. So as I have two sign changes, so I can say that there are two poles out of 8 poles on the right half plane. Now what about the rest of the 6 poles? Now let's see if there is any sign change over here. 1, 2, positive, 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 positive. Again, I can say that all of these are positive. There are, due to S4, there are 4 poles which have the symmetry over the origin. Then again, these all pole, as there is no sign change, so there will be no symmetric pole on the right half side of the plane. So all these 4 poles will lie on the j omega axis. So another information, I 2 poles on the right half plane, 4 poles on j omega axis. What about the remaining 2 poles? Remaining 2 poles on left half plane. So if you had a system in which there are number of sign changes, or there are 2 sign changes in total, it has 8 poles, it has no zero row, there are only 2, so this is a plane. If there is a system which is a plane Routh Hurwitz array, in which you have a simple Routh Hurwitz array with no zero in the first column or the row, and it is order 8, and if you have 2 sign changes and there are 2 poles on the right hand side and the remaining 6 poles on the left hand side. However, in this case, as you have this 0 row, so due to this 0 row, we know that there is a symmetry over the origin, around the origin of these 4 poles. So there is no sign change. It means that the symmetry has no poles on the right hand side. Then the only symmetry for 4 poles we can get around the origin is around j omega axis. So 2 poles over here, 2 poles over here. There are 2 poles on somewhere in the right hand plane, and there are 2 poles somewhere in the left half plane. This is the interpretation of the system. Hence, system is unstable system. So this system is an unstable system. Now let's discuss some another practical example of your how the router. Up till now, you only know how to find the stability of your system using Routh criteria. But Routh criteria is of multiple uses as well. For example, it tells you the ranges of the system, the ranges of the variables of the system, which have the tendency to put your system into the unstable mode. For example, if you have an amplifier and amplifier has a gain K, this Routh array has ability that it can tell you that you can increase this k up to maximum up to x level x. If you move your amplification level above this level x, then your system will become unstable and your system will have a sign change in your first column of the Routh array. So how we can make use of this Routh array in our practical system? For that, let's consider an example. For example, I have this robotic system in which I have a, this is the example from a Norman Nice book, by the way, which is one of your reference books. Controller, there is a robot. For this block controls the head of the robot, head dynamics, and then I have output y of s. Then there is a negative feedback over here, and then the gain of controller is k, let's suppose it is k into s plus a divided by s plus 1, and head dynamics have the transfer function 1 over s into s plus 2 into s plus 3. So we are now discussing a practical example of any system in which we want to see up till which level we can increase our K or we can increase our A. Obviously, there must be some limit over K, beyond which the system will become unstable, and for between that range our system uh, will behave normal and in the stability region. Or you can say that your poles will lie on the left half plane for some value of k, and when your value of k, by the way, from your previous knowledge you already know that your k has the ability to change your zeta, which is the damping ratio, and then zeta obviously changes your characteristic equation, and then the roots of the characteristic equations are also changed. So whenever this k is changed, your roots are changed, your pole location is changed, and when your pole location is changed, it can move from one point to another. So we want to see that whatever movement it have, it should be in the left half plane. It shouldn't move to the right hand side. So uh, for what range it remains in the left hand side, that we can calculate with the help of your Routh Hurwitz criteria. So what can be the characteristic equation for this system? The overall transfer function of this system can be calculated. You already know the equation for a feedback system, G of S over 1 plus G of S into H. I have omitted H of S because it is a unity feedback. So this is the transfer function, and this is the G of S. G of S is K into S plus A divided by S plus 1 to S plus 2 into S plus 3 into S. So you can multiply these and have the characteristic equation as S. Sorry, you can put this G of S in over here, and you can find the transfer function, and eventually you will find that characteristic equation, which I am writing directly as characteristic equation will be S4 plus 6s cube plus 11s square plus k plus 6s plus ka is equal to 0. This is the characteristic equation of your this system. Now let's try to make a Routh array of this characteristic equation. Routh array is S4, S3, S2, S1, S0, then 1, 6, 11, K plus 6, Ka, 0. And what would be in, let's call the variable or the expression that appear over here will be B3, and B3 will be equal to 60 minus K divided by 6, and something that will appear over here is, let's call it C3. Your C3 will be B3 into K plus 6. You have to find this by yourself. Minus 6 Ka, it's not that difficult, divided by B3. And then over here you will get K into A. I'm not concerned with these values over here because it doesn't make any difference. They are helpful to find this C3 and the value over here and over here, but eventually obviously their sign doesn't matter. So what is your goal? Your goal is to find the values for the or the ranges for K and A. From here I can see that K should be greater than 0, because this is positive, this I don't know, this I don't know. In order to have a stable system, if these two terms are positive, then these three terms should be positive as well, because there should be no sign change in order to have a stable system. So if this term has to be positive, then this k obviously should be greater than 0. So from here I can have the leverage to conclude that k should be greater than 0, and obviously a should also be greater than 0. None of them can be 0 or less than 0, neither k or neither a. K and a both should be greater than 0. If any one of these two is less than 0, then obviously this term will be negative, and if this term is negative, then your system is unstable. So the lower range I can find, I have found the lower range for these k and a from this point, from this ka. Now the from here I can find the upper range of k. How? For this to remain positive, this 60 minus k over this should remain positive. So if k is less than 60, then this term is a positive term. However, if k is equal to or greater than 60, then B3 will be negative. So k should be greater than 0 and k should be less than 60 in order to have the stable system. How I have found these ranges? With the help of information from the Routh criteria. Routh says that you cannot make any sign change in this first column if you want to have a stable system. So as these two are positive, first two terms are positive, so I have to take this term also positive and this term also positive, so that I don't have any sign change. Now what about this term? Obviously this term should be positive as well. So from this I have found the lower range of k and a. From this I have found the upper range of k, that k should be less than 60, greater than 0. From C I will find another range for a. So let's put this C3 greater than equal to it should be greater than 0 ideally. So let's put C3 greater than 0. C3 is basically k plus 6 minus 6ka divided by B3. I want to put it greater than 0. So putting the value of B3, it would be k plus 6 minus 6ka divided by 60 minus k. This is the value of B3, 60 minus k over 6. This should be greater than 0. So 60 minus k into k plus 6 minus 36 ka should be greater than 0. 60 minus k into k plus 6 should be greater than 36 ka. So a should be less than 60 minus k plus 6 divided by 36k. Now you can see that the upper boundary of k is of a is dependent upon k. So whatever the value of k you are setting up, your a has to be according to that k value. For example, when you put k is equal to 40, which is between 0 and 60, then your a should be less than 0.639. Put k is equal to 40 in this and you will get this a should be less than 0.639. So in this way you can arrange your variable, you can have your variables k and a in order to have a stable system. So these are all the scenarios for the Routh Hurwitz criteria. We have discussed a practical example as well. One small point which I would like to discuss is relative stability. Now what is relative stability? For example, you have two systems, system A and system B, and you apply Routh criteria to both systems. System A has one pole over here and one pole over, let's suppose, one pole over here, whereas system B has one pole over here and over here, far away from this geomag axis. So, uh, which system is more stable? Relative stability. Up till now, your Routh Hurwitz criteria cannot tell you that either system A is more stable than system B or not. However, previously, obviously, when you were able to find the roots of the system, then you can see from the poles that the farther the pole, the greater margin you have to reach the right half plane. So, the farther the pole, more stable is your system. And if, for example, if your poles are over here and you have some variables that affect the location of your poles, then you have a large margin to reach the right half plane. So your system will not become unstable easily. However, in that case, your system is your one of the pole is already on the boundary, and if any variable changes the location of this pole, it has the tendency to move to the right half plane. So this B is less stable than A. So, however, in Routh Hurwitz criteria, you are unable to visualize this because Routh Hurwitz do not tell you the exact location of the poles. Routh Hurwitz only tells you that either the pole is on the right half plane or left half plane or the imaginary axis. So, what we can do to find the relative stability by using the Routh Hurwitz criteria? This is your problem statement for this topic. Let me repeat that in case when you were able to find the stability with the help of the exact value of the roots, you were able to see that whether the roots are away from the geomag axis or not. Farther the roots, greater the stability. Closer the roots from the geomag axis, uh, lower the stability. So what is this relative stability? That system A is more stable than system B. So how can we find this from your Routh Hurwitz criteria? Now, now as you know the problem statement, the solution lies in moving the geomag axis. For example, or moving the S plane. For example, your S plane are over here, and you have another system. I have drawn two S planes. One of the system has pole over here, or you may say over here and over here, and another system has pole. This is 1, this is 2, this is 3. This is 1, this is 2, this is 3. And another system has pole over here and over here. So now there are two systems, system A and system B. When you will apply Routh Hurwitz criteria on system A, it will tell you that there are three poles on the left half plane. It will not tell you the exact location of those three poles. Similarly, when you will apply Routh Hurwitz criteria on system B, it will tell you that there are two poles on left half plane. However, it will not give you the exact location of those poles. But what if I move these axes? What if I move these axes? For example, if I move this axis to this point. Similarly, over here, I have moved this axis to this point and then again apply Routh-Hurwitz criteria for this red axis for these both systems A and B. Now your RH criteria for system B will tell that system has two poles on the geomag axis and it is a marginally stable system. However, your RH criteria for system A will still tell you that your system is a stable system and it has no pole on the right half plane, it has all poles on the left half plane. So from here you can judge or you can conclude that your system A is more stable because even after shifting the axis to the left, even after shifting the axis to the left, this system A is still a stable system. However, this system B became marginally stable system. One more shifting, let's suppose I have shifted for axis location at 1, for axis location at 2, for axis location at 3. So for axis location at 1, both systems were stable. For axis location at 2, system A was still stable and system 2 was marginally stable. For axis location at 3, system A is still a stable system, whereas the system B is now an unstable system because this is the axis 3 location and your poles lie on the right hand side of this axis 3, and whereas this axis 3 location over here, your poles are still on the left hand side of this axis. So this is the way that we can find the relative stability of two systems, that one system is already unstable if we have moved the axis three times to the left. However, this system remains stable, so hence concluded that this is a more stable system. Example. Let's see, for example, you have a system. Let's take a simple example, S3 s cube plus 4s square plus 6s plus 4. If you find its Routh array, it will be S3, S2, S1, S0 and 1, 4, 6, 4, 0, 0. Let me write directly 5, 0, 0 and 4. It is a stable system. There is no sign change in the first column of the Routh array. So this system is a stable system. Now let's move the axis and have a new axis Sn, which is equal to s plus 1. Sn is equal to s plus 1. New axis are 1, old axis plus 1 means they are shifted to the 1, they are shifted to the left by unit 1. So putting this s value, and from here I can see s is equal to Sn minus 1. Put this in this equation, I have Sn minus 1 cube plus 4 Sn minus 1 square plus 6 Sn minus 1 plus 4. So which is equal to Sn cube plus Sn square plus Sn plus 1. When I will try to make its Routh array, s cube, Sn cube, Sn square, Sn1, Sn0, 1 1 1 1 0 0 1 0. I have a 0 row over here. So from a completely stable system, now this system is a marginally stable system. Now for practice, shift the axis to another one unit and then find whether this system becomes unstable or not. For example, find this Sn minus 2 cube plus 4 into Sn minus 2 square plus 6 into Sn minus 2 plus 4. Find its characteristic equation and then equivalent Routh array, and then see whether the system is unstable or not. System should become unstable. Initial system was stable, shifted by one axis became marginally stable. Now when shifted by two, it should become unstable. This is your exercise. Please do practice. In case of any questions, you may write me at rafe.chotai@uet.edu.pk. So for practice, I received one of the email from one of you. So uh, he asked me about the practice, from where I can do the practice questions. So just do the exercise questions from the back of the chapter in your Dorf book. No need to do any questions which have complex mathematics, because this course in this course you should learn the concepts of the control systems. You should be fluent in the control systems projects. So just do the exercise problems, not do not go to the complex engineering problem design examples. Just do the basic first portion of the exercise problems. In case of any questions in those exercises, you may write it to me and I will respond. Okay ji, thank you very much. See you in next time in another lecture. Allah Hafiz.